Okay, I will continue on more kernel lower bounds. Last time we saw a few problems which we ruled out, kernels which are polynomial in size, disjoint factors, disjoint cycles, vertex cover, clique parameterized by vertex cover, SAT parameterized by the weight and the length of the clauses. These are problems. Essentially what we did was we took t instances of an NP-hard problem in polynomial time, reduced to, I think in all the examples we saw the NP-hard problem was the same as the problem we started off with, well except for the last problem, yeah, the same problem. And the goal of this composition should be that, or it was in all those cases, k was simply a polynomial in the input size. It had zero dependence on t. It had a dependence of log t. Right? In the case of SAT or disjoint factors, the parameter increased by k became k plus log t. Okay, so the dependence on t was t to the little o of 1. So this rules out if I had t to the little o of 1 times this, then rules out any polykernel. Okay. So this is t to the little o of 1, different from little o of t. Okay. I hope you these two are different. Last time we had log t was the dependence, and that's t to the little o of 1. So what would be an example function which is here but not here? So square root of t, for example, is little o of t, but it's not t to the little o of 1, because I want the exponent to be not a constant, a decreasing function of t. Okay. So a square root of t is not t to the little o of 1, but the general theorem we saw that whenever we had dependence on t like this, then it rules out and the examples we saw last time had either no dependence, k went, parameter went to simply polynomial in the input size, or there was a log t dependence. Okay, and so that ruled out any polykernel. But today we are going to look at a couple of examples where all we can do is to make the parameter go to square root of t times the input polynomial in the input size. And so that will rule out k power 2 minus epsilon polykernel. So depending on the problem, either it's a very good result or a not so good result. If we didn't even know there was a polynomial size kernel, then ruling out k power 2 minus epsilon kernel is sort of weak, okay, because I really would like to rule out any polykernel. But if I had a k square kernel, then k power 2 minus ruling out k power 2 minus epsilon makes it really tight. In fact, so we will see an example of each kind. So the first problem we're going to look at is called in this name. So the input is graph G, undirected graph. The parameter is k. The question is, does G have an independent set or a clique of size k? Okay, so this was, I believe, in the problem sheet. I don't know whether anybody solved this. Saket, we included in the problem sheet, no? Ramsey? Clique or independence, I remember. Yeah. So we know that finding a clique of size k is W1 hat, finding independent set is W1 hat, but if you ask the question, give me either one, it turns out to be FPT. Okay. Any idea why? Like, the name of the problem should give you a hint. So it's let's make some observations about it. Problem is in FPT. So why is it FPT? Ramsey theorem tells you that if you have a graph with at least RKK many vertices, then the number of vertices is at least RKK, then the answer is yes, you will have a clique or an independent set. Right? In fact, you can actually convert that into an algorithm as well. Else, we have a kernel, right? You can. I mean, okay, I'll come to that. Okay. Else, we have a kernel and do some brute force. And the size of, because this is pure function of k. Okay. So right now we still don't know exact bound for RKK. We have some lower bounds and upper bounds. So you take your lower bound or upper bound, if you like, and go with that. So that function is about 2 power k square or something. I think 2 power k choose k or some such thing. Else, we have a kernel. So you can just do brute force. So converting into an algorithm again, you can focus on a subset of this many vertices, do brute force. Okay. And you know there is a clique or an independent set. So is it clear? So that's FPT. RKK is pure function of k, and you have some bounds. So look at the graph, and if I have that many more than vertices, then I just focus on a subgraph of that many vertices, do brute force, and I know that I will find it. Even otherwise, your number of vertices is bounded by a function of k. Okay. So this is surprising that we know. Well, I don't know. Clique. Finding clique is W1 hat, finding independent set is W1 hat, but if you ask for any one, it's FPT. First of all, is it NP complete? Let's quickly check that as well. So there's some easy reduction from clique or independent set. Basically, you can say this is as hard as finding a clique or independent set. Anybody has a, yeah? Mm-hmm. Okay. So we want to reduce from which problem? Clique, okay. Clique instance. So now you take your graph G, add n more vertices, make it a clique. Yeah, okay. So make this a clique. So size of V is n. Okay, and add all these edges. Let's call this G prime. G has a clique on k vertices if and only if G prime has a clique or an independent set on n plus k vertices. Right? There is no independent set of size n plus k here at all. So you give you a Ramsey question, tell me whether there is a clique or an independent set. If the answer is yes, the only reason is that there is a clique on k vertices in G. Okay. So we have an exponential kernel, and it's known that actually that this problem does not have a polynomial size kernel, but I am not going to give that full blown polynomial kernel ruling out. I am going to give you a k power 2 minus epsilon kernel. Before that, this problem is not just a toy problem. Okay, so it comes up in some more general problem. Suppose I ask the question, let's say, does G have, let me erase this, a perfect subgraph induced on k vertices? Okay, so given this graph, I want to find some property, perfect caudal graph, interval graph or something. I am interested in maximum induced perfect graph in this graph. Okay, if you don't know what perfect is, don't worry about it. Caudal graph, if you want to think about it, some property. Now this is different. So parameter is k, the size of this graph, which I am after. This is different from asking, can you delete k vertices to get perfect graph or whatever, right? That's sort of easy because you saw it in the first problem sheet that if you have a hitting set, you can look at it and say, okay, this is something I want to hit. So I can say one of these vertices must be in the deletion set and branch, right? This doesn't give you a way to branch because you are looking for a subset. Okay, but turns out you can use something similar to show FPT, similar idea. So what is it? That observe that an independent set is a perfect graph. Okay, perfect graph is a graph where there are no induced odd cycles of length phi. Okay, an independent set is a perfect graph. A clique is a perfect graph. Okay, so if the graph has this many vertices, then yes, there is a perfect induced subgraph on k vertices, because there is a clique or an independent set. Otherwise, brute force. Okay, so it's just sort of a core, but a lot of problems can be shown FPT using this similar idea. So, okay, so the goal now is to show that this problem does not have k power 2 minus epsilon kernel. We are going to take t instances of an NP-hard problem, which will turn out to be a version of this problem, not exactly this problem, and reduce to this problem with a square root of t dependence. Okay. Now, so we are going to do something similar to a composition, disjoint union, or add all possible edges, and so on. And it's a problem about clique and independent set, and we encountered this problem in my first session on kernel lower bounds. We were trying to show independent set parameterized by tree width, and somehow I want k to go to something, and we came up with an intermediate improvement version, and that was useful. That assume the graph has an independent set of size k and look for one of size k plus 1. That turned out to be useful because the witness that there is somebody of size k in each of these instances is going to be helpful for me. Okay, so we're going to start with a similar improvement version for this problem. So let's call this improvement Ramsey, where you are given graph G and I, an independent set of size k, C, a clique of size k in G, all this in G code. And the question is, does G have a clique or an independent set of size k plus 1? Okay. So, this is the problem. I assume that I give you a click and an independent set of size k and ask is there one of size k plus 1, any one of size k plus 1. So, this is the problem we are going to compose to and start from. So, first we have to show the problem is NP hard. Okay. In fact, I realized that some of the problems we did last time I forgot to prove the starting problem NP hard, in particular the disjoint factor. Okay. It is a nice exercise to show it NP hard, the acute reduction from 3 SAT or something. So, we are modifying this problem. So, let us try and first show this problem is NP hard. Okay. This is also not very hard. We will reduce from this problem, the standard Ramsey problem, very similar to the kind of reduction Sajin was telling. So, NP hard. So, what we are going to do, reduce from the Ramsey problem. So, here is a graph where you want to know, the question is there a click or an independent set? Let us say k plus 1, and I want to reduce to an instance where there is a click and an independent set of size k, and I am asking the question is there one of size k plus 1. Okay. So, that reduction is going to be something similar. Now, you have to also add a click and an independent set. So, I add k size independent set, k minus 1 click, so, and all these edges. Okay, so that is my G prime. There is an independent set of size k, there is a click of size k minus 1, and I add all edges. The independent set is adjacent to everybody there as well as here. The graph clearly has a k sized independent set, right? Where is the k sized independent set? Let me call this. Where is the k sized independent set?
Independent set and any vertex here.
Actually, there is a k sized independent set. Where is the k sized click? Yeah, take the k minus 1 click and take any one vertex from here. So, there is a k size independent set, there is a k size click. Now, I claim that G has a click or an independent set of size k plus 1 if and only if G prime has. Okay. Can be, but maybe there is only one vertex can be or something. So, I do not know whether I should say k plus 1 or k here. K plus 1, let us see. So, the claim is this is G prime, this whole thing is G prime. G has a click or an independent set if and only if G prime has of size k plus 1 okay. If okay, so forward direction is easy because it's G is a subgraph of G prime. So, if G prime has a click or an independent set of size k plus 1, let us say it has a click of size k plus 1, that click I claim should come entirely from G, because you can at most pick one vertex from here, so that does not help. So, it can pick one vertex from here. So, that is why I think k, I want to, I think this is k. Yeah, this question is k, because now, okay, so then let us go through the forward direction also. If there is a click of size k, take that and take one such vertex and you have a click of size k plus 1. There is an independent set of size k, take that and take one vertex from here, you have a k plus 1. Conversely, if you have a k plus 1 sized clique, the clique can pick at most one vertex from here really. So, the k guys should come from here. Similarly, if there is a k plus 1 independent set, again you can easily see that it can pick at most one from there. So, k should be here. At most one from the clique may be there in the k plus 1 size independent set. Okay. So, the improvement version is NP hard, and that is the problem we are going to reduce from.
But it's already given that G has a independent clique of size k.
Yep.
What's the question?
Here it is k plus 1.
No, in the question, improvement terms.
I know.
That is k plus 1.
Oh, sorry. Okay. Oh, I shouldn't have changed this question. What I meant is this. Yeah. G has a clique or an independent set of size k if and only if this has one of size k. Okay. This is a statement of the problem. Okay. I was changing in the reduction. Okay. So, now we are going to take key instances of improvement Ramsey. So, what that means is you have G1, K, well, yeah. So, you have T graphs, each has a clique of size k and an independent set of size k, and my goal is to know whether there is a clique or an independent set of size k plus 1. Okay. That assuming that all these graphs have, let's even assume that every vertex has n vertices, they all have cliques of size k, they all have independent sets size k. Making that assumption is what is possible by this equivalence relation definition, because now I am going to assume that two graphs are equivalent if they have the same number of vertices, they have a clique of size k and an independent set of size k. Okay. Then all the properties of the equivalence relation is satisfied, and so that is the little technicality we went through for in the notion of equivalence classes. Okay. So, now I am going to give you a graph here. In polynomial in n times t, I am going to give you a graph G prime with the parameter k such that, what is the property we want? G prime has, I do not want to call it k, k prime, a k prime sized clique or independent set if and only if, what? One of the instances, if and only if there exists I such that Gi has a k clique or a k independent set, k plus 1. Yeah. Because the problem here is looking for a k plus 1 sized clique or an independent set. And what do I want with respect to k prime? To rule out k power 2 minus epsilon kernel, I want k prime to be at most t power half, yeah, square root of t times k, or some function, some I don't want k, sorry, right? Not necessarily, yeah, some polynomial in n is good enough. Square root of t times some polynomial in n. It turns out to be, I am going to say, yeah, this is what I am going to say. Right. So, in the case of independent set parameterized by tree width, we had this t instances, and finally we said they all have one of size k, and so tk plus 1 is what the bound we were looking for if and only if one of them as k plus 1. Okay. And that was okay at that point because the size of the solution was not the parameter. We were looking at tree width as the parameter. But here, the size of the solution is the parameter. So this is the goal. Okay. Now, the construction of G prime is fairly straightforward. So G prime, what we are going to do is divide these T instances into square root of T groups of, okay, so I'll have G1, G2, G square root of T in one group. In another group, and finally GT. Okay, I mean, it goes without saying that square root of T is an integer, and otherwise we'll add some dummy instances and make it that many instances. So what I'm going to do is so each one is a graph, right? I'm going to add all edges between every pair of them here. But across groups, I'm not going to add any edge. Okay. So these are graphs. Add all odd edges between vertices of graphs in each group. And then this is my whole G prime. Okay. So the property of G prime is that if you sort of contract every graph to a single vertex, then every vertex is in a clique of size square root of T, and also an independent set of size square root of T. Think of each graph as a vertex, contract it to a graph. Okay. So all I'm doing is a root T clique here. It's a bunch of root T cliques. Every vertex is in a root T clique and also a square root of T independent set. Okay. And this is, I'll come back to this property of this graph later. But so now let's just go back and verify that this is true. Okay. So if some graph, so every graph now I know has a clique and an independent set of size k, right? So root T k clique and root T k independent set is guaranteed for me in G prime. In G prime, I take the clique from every graph. So this graph has a clique of size k, k. So totally square root of T times k clique is there in this whole graph because I've added edges across every graph in each group. Similarly, an independent set of k times square root of T is guaranteed because I take an independent set from here, independent set from here, independent set from here. That much is guaranteed. So it's the extra plus 1 which I get if any one of them has a clique or an independent set of size k plus 1. Okay, and that's also follows really that if some graph, let's say this graph has a clique of size k plus 1, then this whole thing has a clique of size square root of T times k plus 1. And similarly, if your graph has an independent set of size k plus 1, this one has an independent set, then pick one, all of this, and they will give you an independent set of square root of T times k plus 1. That's a forward direction. Conversely, if you have a clique of size square root of T k plus 1, then Yeah, there, I mean, you can get a click only in a group. So one of those graphs have a click of size k plus 1. And similarly, if you have an independent set of size this, then you cannot get two graphs from a group into an independent set, because there are edges across between everything. So it has to be one from here, one from here, one from here. So that's the maximum click independent set you can get, and so it follows. Okay, wait. So let's see how many vertices are there in this graph. That's n times t. Right? I just put together everything. So that's okay, because this reduction I did not bother about the size of the instance. It was the parameter which was important to me. Okay? The size of the instance is polynomial in the input size, and the parameter now goes from k to square root of t times k. Yeah, you had it.
Yeah, so just a small remark that here adding dummy instances might not be that easy because you want to add graphs.
No instances of
Yeah,
Ramsey.
so no instances, adding them might not be easy. So even adding no instances.
Okay.
Because you want to find a graph on n vertices which does not have a click or independent set. So instead of doing that, you just repeat the instances so that the number becomes.
Yeah. Mm-hmm. Yeah. Yeah, this is again a general trick you can apply anywhere, not just adding no instances, you can add repeat. Yeah. Okay, so now to rule out polynomial size kernel, I want this square root of t to become t to the little log t or something like that. So think of what we are doing is we are taking these t instances and we are mapping to a graph like this. This was a graph which is just a collection of disjoint root t clicks, and the property I was using was that every vertex is part of a click of size square root of t or an independent set of square root of t. So to rule out t to the to get t to the little o 1, you need an appropriate graph here, and it turns out you can use this cone non-determinism allowed in this whole Fortnow Santanam lemma. So non-deterministically, you can find such a graph and embed and rule out poly in k kernels, not just k power 2 minus epsilon. And then the other comment is that, remember I said this problem is just not a toy problem, it has a lot more. You can talk about finding any hereditary property like a click, not click, but a perfect graph, caudal graph, and you can ask the kernelization question there as well. Okay, it doesn't follow directly from any of this because that is a very specific question you are asking, and that problem is not completely resolved, but I think there is a result which says that for most properties which are FPT to find, you can rule out polynomial size kernels, but not, there is no one single theorem which rules out every property. Okay, does that make sense? No? No. So let me just say what the because this is a okay. So much on Ramsey. Now I'm saying you can look at the following general problem given G and a parameter K, and let's say pi is some hereditary property. And the question is, does G have an induced subgraph G prime on k vertices such that G prime is in pi? Okay. This is very similar to the deletion problem which we looked at, where you want to delete k vertices to put the graph into pi. Here I am asking, can you find k vertices that induce a graph on pi? Now, this is not always FPT. Do we know examples where this is hard. What do you mean by always? I mean, choose a property pi for which this is hard. Click. If pi is all clicks, that's a hereditary property, and we know that this problem is W hard. Okay. So now there is a very nice characterization known on properties of pi for which this is W1 hard and this is FPT. Okay. When is this FPT? When is W1 hard? There is a dichotomy theorem known. Now, one can ask the kernelization question on the properties which are FPT. Okay. So, what I was saying is that that question is more or less resolved with the answer that most of those properties do not have polynomial size kernel, very similar to this Ramsey, either through a reduction or tuning the proof of Ramsey to push it to these properties. But there are still properties which are FPT, and we do not know whether they have a polynomial size kernel or not. Okay. So, now let us move on to the next problem, which is vertex cover. Okay, so your vertex cover problem, given a graph G, you want to know whether k vertices that cover all edges. We know a k square size kernel, many k square size kernels, like different kernelization algorithms, and we want to rule out k power 2 minus epsilon kernels, and the strategy is going to be very similar. Take t instances of some NP hard problem and reduce to a graph with the parameter k prime going to be something like square root of t times the polynomial in the input size, and G has this G prime as a k size vertex cover if and only if you have an S instance for the starting NP hard problem. Okay. So, NP hard problem which you are going to start with is going to be actually a version of a click problem. It's actually a click problem on a very structured graph. Okay. So, what is that problem? It's a multicolored biclick. Okay. So, given a bipartite graph where the vertex set of each part is partitioned into k of k such parts. So, think of it as k colors. Okay. So, you have the question is, and is there a so it's a bipartite graph, so that I just here. Is there a biclick with on 2k vertices with all vertices having different color? Let's say all these colors are distinct, 2k colors. Okay. So, I am looking for a biclick, that means a complete bipartite graph on 2k vertices. So, one from all these 2k vertices should come one from each of these 2k color classes. Okay. All right. So, another way to think about it, because I am going to view it as a click problem, is draw all edges. So, this is a bipartite graph to start with. I am going to now draw all edges between every pair of color classes. Okay. Then this question is same as what? Is there a click of size 2k in this? No, so, not any more bipartite graph. Yeah, I will just come to that. Yeah? Original problem? Okay. The problem is you are given a bipartite graph, UWE. Okay, where each vertex in U has one of k colors. Similarly, each vertex in W is one of k colors. Let's assume that all the colors are different. Okay. In other words, the vertex set is partitioned into k parts, each of them. Okay. Now I am asking, is there a bi-click, a complete bipartite graph with 2k vertices where the color of every vertex is different? It's a colorful bi-click, if you like. Okay. Now I'm saying now I'm going to make the problem simpler, or like just like a click problem. So what I will do is yeah, 2k colors. Yeah. So now I'm going to forget about colors, right? So I'm going to now change the instance into a k partite graph in each side. So it's no longer an overall bipartite graph. So add complete gap, add all possible edges between every pair of color classes here alone, and similarly here alone. Now I ask, is there a click of size 2k in this graph? Right? So that click, yeah. Yeah, now I've removed the colors. Okay, so now I've removed the colors. All I've made sure is that there is all possible edges between every pair of the color classes in each part. Once I have done that, now if I look for a 2k size click, how will it look like? Right? It has, because each one is an independent set. So it has to come one from here, 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 and it's so in this portion it must be a bi-click. So we'll think of it as just asking for a 2k click in a structured graph like this. Okay. First, let's try and show that this problem is NP hard. Then we will do a reduction from here to give a composition. Okay, so why is this problem NP hard? So we're going to reduce from click to my G prime, which is going to look like k pieces here and k pieces here. So k copies of G. So each one is a copy of G. Copy of V of G. Not quite the edges. So I take the vertex set of my graph and I make k copies of each one of them, right, in both sides. And my edge relation is going to be, if you have a vertex u and a vertex u, I will add an edge in the same numbered copies. So 1, 1 is going to have this, yeah. So it's like a matching. Okay. So this is copy number 1. Copy number 1 here, the vertices u is adjacent to u, v is adjacent to v, and so on. Basically, the edges are only between their copies. But if you pick a vertex here and a vertex here, I'm going to add an edge if they are adjacent in the original graph. Okay. So let me say it here. So let's call this v1 and v2. So u is adjacent to u. Okay. So u in vi is adjacent in, no, I should call this v11, v12, and v1k, and this is v21 and v2k. So u in v1i is adjacent to u in v2i. That's one kind of adjacencies. And then I say u in v1i is adjacent to V in V2j, where I is not equal to j, if uv is in H. Okay, I'll let you read and parse this, and I'll come and explain. Then the claim is that G has a clique of size k if and only if this G prime has a clique. So I'm going to add all edges here. Then G prime has a clique of size 2k. Okay. So between same copies, only the corresponding vertices are added, the adjacency, and across copies, you add an edge if this u and v are adjacent in the graph. Okay.
Different copies in the same side all have all edges.
They have all edges.
Yeah, all edges between them.
So
That's
if I have a k-click,
okay. So let's just go through, right? If I have a k click here, then I want to claim a 2k click here.
isn't there already a k-square click here? Just take these. It's a k-square. No, but everything is connected.
No, and across things are not connected everything. That is, across is depending on the adjacency of the graph. Yeah, within here, everything is connected. So that can give you a k click, that's all. It can give you 1, 1, 1 k click. Now, if you want to go and grab here, maybe a k plus 1 click, that's all you can get. Actually, not even k plus 1 click. You can guarantee a k click, that's all. Now, I claim that G has a k click if and only if G prime has a 2k click. So if G has a k click, what I will do is pick one of those vertices from here, one of the another vertex from here, another vertex from here, and so on. And similarly, the same kind of vertices here. Then I claim that that would give me 2k click. Why? Because within them, that's all edges are there, and across, because of the corresponding thing, I'm picking those vertices to show edges across. Because it was a click, you had this neighborhood relation telling you these edges are there. And on converse is pretty much you can reverse this proof. If you have a 2k size click, it has to be one from here, one from here, one from here, one from here, and because of these across edges, those k vertices must form a click. Yeah. Okay. So this problem is essentially a click problem on a structured. You can think of it as a biclick in a colored graph, or just a click problem on this kind of a structured graph. So now I want to do some embedding of T instances into yeah. So now you're given the composition. You're given G1, G2, GT, T instances, and I'm interested in a k click in each of them. Right? So it's a question is there a k click? So each graph is looking like that. Okay? Each graph is looking like a bipartite graph, if you like, with k colors. It's looking like this. Okay? Let's make this extra assumption that the sizes of each of this, they're all the same in each of the instances. Okay? We'll add some dummy vertices otherwise to ensure that. So now this is what's going to help us to combine this. Okay? It shows up again in many composition. So what we'll do is we'll construct the following root T by, so I'll have root T vertices are parts. And each one is this k-sized. So think of this as a, in all, see the point is that in all these t instances, the left side and the right side are the same, identical. There is no difference, right? K different parts with complete all edges across them. It's just the edges between they are different. Okay, that's what I'm going to exploit now. So, right, make these root t copies of the left side here, and similarly the root t copies of the right side here. Now I have to draw edges across. Can you guess how I'm going to do? Sorry. Yeah. So I have t instances of graphs of that type. What do I mean by that type? That it's a, there are 2k parts to the graph, k this side, and there is an edge between every pair of vertices across these parts here, similarly here. Okay? That's how every graph of the t instances look like. Where they differ is the edges across. Okay? So that other than that, these guys are exactly the same. All these t graphs are. Okay? Now from these t graphs, I'm going to come up with one single graph, which is somehow going to embed all these t graphs. Okay? And so this is going to be part of my composition. So what is this one big graph? The one big graph I'm going to construct has root t copies of the left side here, and similarly the root t copies of the right side here. Now I am to draw edges. So let's think of, so this is L1, L2, L square root of t, and this is R1, R2, R square root of t. Now I'm going to draw edges across them. That's going to be dependent on how the edges are in these t graphs. So what should I do?
Size of each partition being same as
Yeah. Size of each partition is
size
same.
of each the number of
Yeah, then this is k, right? The number of such parts is k. It's exactly identical to the left side of each of these GIs. So I'm just made root t copies here, root t copies here. Yeah. Now I'm going to embed my graph, these t graphs, into this graph finally. Okay. So the embedding is very natural. What do? I take my, right. So I have lots of room here. So an Lij, I take Li, Rj, for every possible I and j, I can draw edges between them to reflect one graph. How many different graphs can I get in this process? T different graphs, because I has square root of t choices, j has square root of t choices. So totally t different graphs. So I take each graph and say, okay, G1 is going to be, I'm going to draw edges between L1 and R1. G2 will be maybe L1 and R2. G3 would be L1 and R3. And G root t will be L1 and R square root of t. I will draw edges exactly like the way they are appearing in that particular GI. And I do that for L2, L3, and so on. Okay? So that's my, this particular graph. Let's call this G prime. Is G prime clear? So I've somehow embedded all the t graphs, not in nt vertices. How many vertices I've used?
R2 is a different graph than R1.
R2 is a copy of the right side. All the right sides and all the left sides are the same of every graph anyway, right? So I'm just using, instead of needing n times t copies, how many? Sorry? I'm constructing. There's no edge. I'm saying so I'm going to take G2. How does G2 look like? G2 is some k pieces here, another k pieces here, and the edges are sort of different. So I'm going to go and say, okay, this graph I'm going to draw in L1 R2. I've just decide that my L1 R1 is going to embed G1, L1 R2 is going to embed G2, L1 R square root of t is going to embed G square root of t, and then I take L2 R1 and do the next graph, and so on. Okay. So instead of n times t vertices, how many vertices I have used now? 2n times square root of t. N times square root of t and n times square root of t. So 2n times square root of t. So I have embedded all these graphs. Sir?
N times square root of t because
Oh, okay, yeah, sure. A pair constitute n vertices. Okay. So n times square root of t vertices. So now what is the property in G prime? I want to claim the following, right? That's what finally I would say, that G has, okay, so G prime has n times square root of t vertices, right? Or assuming every vertex set, every graph has n vertices. Now here is my claim. G has a clique on k vertices if and only if G prime has, no, sorry, not G. There exists I some Gi as a clique on k vertices if and only if G prime has a clique on k vertices. Okay. The forward direction is clear because every Gi is a subgraph here. I have embedded every Gi into this big graph. So if some, let's say Gi has a k clique, that what is Gi? Gi is going to be maybe L3 or 4, let's say, right? So there is a k clique sitting here, that k clique would sit in this graph as well, right? Now conversely, I want to argue, this is always the problem in this composition, right? The two graphs don't combine together and give you a bigger clique, and they won't, because I have ensured that all these parts are different. There are no edges across these parts. So if G prime has a clique on k vertices, it has to come from a piece like this. It cannot come from something here and something here because there are no edges across. It has to come from one piece of Li and one piece of Ri together. So that has to reflect to be a clique in some Gi. Okay, nice composition for clique. But clique was not the problem we wanted to solve, right? You're not done yet. So, but that's okay. We know a close relationship between clique and vertex cover. What do we know? So G prime is not going to be my graph. I'm going to say if and only if G prime complement has an independent set on k vertices, which is if and only if G prime has a vertex cover on n minus k vertices, where n is the total number of vertices, which happens to be n times square root of t. Okay. So what we have taken t instances of some NP-hard problem. In this case is a clique composed to a graph G prime bar with the property. So it's, I mean, all the construction was all polynomial time. We spent only polynomial in the total number of vertices with the property that G prime has a vertex cover. The parameter now has gone from k to n times square root of t. Okay. All we care about is square root of t times some polynomial in n. Okay. So that rules out k power 2 minus epsilon kernel for vertex cover. And also for feedback vertex set, it turns out, because there is a very simple reduction from vertex cover to feedback vertex set, an NP hard reduction. So you can take right, you have a G K vertex cover to G prime. Turns out K remains as K. What is that reduction? So yeah, you can make a parallel edge for every edge and make cycles. If you want a simple graph, subdivide one of the parallel edges and make it a triangle and so on. So G has a vertex cover if and only if G prime has a feedback vertex set of size. The beauty is that K remains as K, right? So what I can do, for example, is go one more step from G prime bar, do this reduction, get a feedback vertex set instance. K remains whatever, the same parameter. Now I have the same thing. I started with click, some NP hard problem, and reduced to a feedback vertex set problem with parameter n times square root of t. Okay. It turns out you can do more reductions and essentially show that for every k deletion to pi, right? Look at the hereditary property and say, can I delete k vertices to get into that property? Pi has no order k power 2 minus epsilon. Okay, so I think I will stop here. Any questions, comments? Yeah.
So these lower bounds are basically, so how do we get that the k square is lower bound on the vertex cover for the, so it's basically it's talking about the bits, right?
Yeah.
And how to distinguish between
Vertices and I don't know really. Sakadina, the lower bounds are talking about the sizes of the kernel, which is sort of the number of bits. Now, is there any refinement to talk about lower bound for the number of vertices versus edges? I mean, it just says the total. Yeah, it's talking about edges.
For example, at least it tells you that the number of vertices cannot be little of k, for example.
Sure.
Right? If it
Yeah.
This, right? So I mean, in that sense, this can only any of these things can only talk asymptotically in that sense. So this lower bound also tells you that asymptotically you cannot have little of k. But there are ways to, like for point line cover where you can do more fancy things and come up with the lower bounds also on points, because that is what is more
On points. Also, there is this lower bound can be tuned for even Turing kernels kind of thing. I remember.
Yes, but only with n to the power little of. We cannot rule out big O of n, like
N to the power little o 1. I see.
or I think n to the power 1 minus epsilon or something.
No, so we can talk about Turing kernel. The example I gave was this. Yeah, multiple kernels. So can we rule out polynomial in n? So there is n and k. So you cannot have one kernel of size poly k, but maybe I am able to give n kernels of size poly k. So can that n? Yeah.
This general result is not straightforward. No? We need
This is not straightforward. Yeah, you need very tight reduction. That k going to k thing was.
But it's still there. I mean,
Yeah. Okay. So that's the end of lower bounds on kernelization. Okay. Thanks.
I think the copy will be just outside.
Here.